In this video, we will go over an example of maximizing volume. In this example, from a 15 centimeter by 15 centimeter piece of cardboard, square corners are cut out so that the sides can be folded up to make a box. Express the volume of a box as a function of side x in centimeters of a cutout square. So we know that the volume of a box is length times width times height, but we want to represent these using just x. Over here we have a piece of cardboard that is 15 centimeter by 15 centimeter. Because we're cutting off the corners of length x, this side right here, x is cut out twice, so the distance from here to here is going to be 15 minus 2x. Similarly, for this piece, the length is also 15 minus 2x. Now, if we fold all the sides up, we're going to end up with a box like this. The height of the box is x. The width of the box is going to be 15 minus 2x. And the length of the box is going to be 15 minus 2x. So the volume is going to be 15 minus 2x times 15 minus 2x times the height, that is x. Next, we're asked to find the domain of the function. In terms of length, we know that length has to be greater than 0. So for the height has to be greater than 0. That means x has to be greater than 0. The length also has to be greater than 0. So the length was 15 minus 2x. It has to be greater than 0. The width is also greater than 0. Now the width is the same thing as the length, so we're just going to write that once. Now let's solve for x. Subtract 15 from both sides. Negative 2x is greater than negative 15. Then divide by negative 2 from both sides. X is less than positive 15 over 2. Remember that when we divide by negative, the inequality sign changes. So the domain is that x is greater than 0, but less than 15 over 2, using interval notation 0, 15 over 2. Next, we're going to use the graph of a function to determine the dimension that yields the maximum volume. Know that x represents the height of the box. So in order to do this, we're going to go on the calculator, and then we're going to input the function that represents volume, 15 minus 2x times 15 minus 2x times x, and then press graph. Notice the graph looks kind of strange there. What we're going to do is we're going to adjust the windows a little bit. So let's go to window. Remember that our domain goes from 0 to 15 over 2. So we're just going to go to start at x min is 0, and then x max, we're going to put in 15 over 2. And then let's take a look at the graph. That still look kind of strange, right? So that means we probably need to adjust the y, the windows for y. For y min, the y represents the volume, and volume cannot be negative, so I'm going to have 0. And then for y max, I'm just going to increase that to 100 and see what it looks like. It looks like I need to increase the y max a little bit more, so I'm just going to increase it to 1000 and see what it looks like. There we go. So the graph looks like this curve. Let's draw that out here. The graph looks something like this. Okay, and we want to know the dimension that would give us the maximum volume. The maximum value of the maximum volume is at this location, but we need to know where that is. So what we're going to do is on the calculator, go to second, trace, and then go for maximum. We're going to go on the left side of the maximum press enter, and then go to the right side of the maximum. Press enter and then enter one more time, and the calculator will tell us the location at that point, 2.5 comma 250. All right, so the x, which represent the height, is 2.5 centimeter. The length, which represents which is represented by 15 minus 2x, that's 15 minus 2 times 2.5, and that gives us 10 centimeter. The width is the same, 15 minus 2x, so it's going to be 10 centimeters as well.